Hey everyone, I want to take this opportunity to walk you through a dynamics problem where we're looking at various forces acting on, in this case, a shovel, and the object accelerating along the surface. Right? So in a problem like this, you're dealing with multiple forces acting on an object. There's an acceleration, which means there must be a net force that's acting on it in order to cause it to accelerate. And all these forces are acting in different directions, so we have to factor in what we know about vectors to make sure we keep everything organized when we're adding these forces together. So we've got a shovel that's being pushed along the ground. It's being pushed at an angle, meaning the person pushing the shovel is kind of pushing down and to the right as they push the shovel into the ground, and it's accelerating to the right. Let's start with a picture to get an idea of what's going on. So I'm going to draw the shovel. That's the object that has mass that we're analyzing. That shovel is on a surface, so I can draw that surface. Clean that up a little bit. And that object has a weight. So the first thing we always put on a free body diagram is our force due to gravity, right? Fg. Fg is also known as our weight, or Fw. And in this case, they tell us the shovel weighs 20 newtons. Again, if you see newtons, they've given you the force. So 20 newtons would be the weight. So Fg is 20 newtons. That's how long the arrow is, and I drew the arrow down. So when I use it as a value in my calculation, I'll actually use it as negative 20, so it's downward in the y direction. All right, so there's Fg. I also am given a friction force. They give us that the friction with the ground is 15 newtons. Well, I have to keep in mind what direction the shovel's going. So I like indicating that the velocity will be to the right, and the acceleration of this object will also be to the right. So if an object's velocity is to the right, or if it wants to move to the right, friction will always oppose that motion. So I know friction's going to be to the left here. Right? And that would be the force of friction. And I'll label it as 15 newtons. That's what it's given in the problem here. Again, it's to the left, so I'll use it as negative 15 later on, but the length of the arrow is 15. All right, we have an applied force that's acting on the actual handle. That's the person who's pushing the shovel. And as you can imagine, if you're pushing on shovels, some of that force is being directed downward and into the shovel. All right, and it's being directed as an angle. So that's the applied force. And they tell you there's an angle of 50 to the horizontal. So if this is the horizontal, then there's the 50 degrees to the horizontal that applied force is being pushed on the shovel. And we're on a surface, so in addition to friction, since it's trying to move, we always have a normal force. So that normal force acts upward, and it's the force of the surface pushing back on the shovel. Right? And that's what keeps the shovel on the surface. Right? So it would either go through the surface or float away if that normal force wasn't just the right amount. You can think of the normal force as what a scale would read. And in this case, if you're just standing on the scale with nothing on you, the scale would read what your weight is. So Fg and Fm would be the same length. But if it's being pushed downward, it'd be like it's carrying something, some extra weight. And so the scale would actually read more. So that arrow for Fn has to be bigger than the gravity force, the weight, in order to keep this shovel on the ground. So that's what our free body diagram looks like at this point. We have 4 different forces, and we know it's accelerating, so there should be a net force in the direction of the acceleration to the right. That acceleration we can actually calculate. So let's do that right now real quick. That'll be the acceleration that's actually in the x direction. I'll kind of define my coordinate plane. We'll call that the positive x and that the positive y. It's a good way to start. And they tell us that it goes from rest to 2.5 meters per second in 1.5 seconds. Right? And we had an equation from our kinematics that said that v final equals at plus v initial. And we can plug in what we have. V final is going 2.5 meters per second. The acceleration we don't know, but we do know that time happens in 1.5 seconds, and it starts at rest. And so when I want to solve for A is just going to be 2.5 meters per second over 1.5 seconds. You get meters per second per second. And in my calculator, I'll put 2.5 divided by 1.5. I get an acceleration of 1.67 meters per second squared. So that's acceleration of this shovel along the surface. Now let's start setting up our second law equations. So Newton's second law says that the sum of all forces acting on an object, in this case all four of those forces, the net force, is equal to the mass of the object times its acceleration. Now, because all these forces act in different directions, we want to try to organize our work, and just like we did with projectiles, we're going to treat all the forces that act in the x direction with other elements that are in the x direction, and we'll treat everything that's in the y direction with other elements that are in the y. So I kind of can break down Newton's second law into two directions. We'll treat the x direction and the y direction. And in this equation, we have different variables. We have the mass, we have the acceleration in the x, and we have all of our forces in the x direction. We know we have friction, force of friction, and that friction force actually points to the left, so I'll put it as negative 15 newtons. All right. We also have the applied force acts partially in the x direction. And on my picture, really that applied force has a piece that's applied downward. That would be the applied force in the y direction, and a piece that's applied horizontally. That's the applied force in the x direction. Now, they're effectively what FA is if we break it into its component pieces. And so the piece that's in the x direction would be the applied force in the x, and I can do some trig to isolate that. So FA in the x, just like when we did projectiles, would be the adjacent side to that angle. So we're dealing with the cosine function, would be FA cosine theta, and FAY would be FA sine theta. Now in this case, I don't know what FA is, so really I don't know what those values are. So I'm just going to hang tight here and see if I can find what FAX is and work backwards from there. In most problems, you're going to be given what that applied force is. In fact, when we did this with the shovel in class and with our web assignment, they told us that applied force. But in this case, I don't know. So I'm just going to leave it blank right now. I could put FA cosine theta in there if I wanted to, but I'll leave it where it is. In the y direction, we have the mass again. We have the acceleration in the y, and we have three forces. G, which is given to be 20 newtons downward, so negative 20 newtons. You have the normal force, which we don't know. We have the applied force in the y, which we also don't know that. We do know the accelerations, though. In the y direction, the shovel is remaining on the surface, so it has zero acceleration in the y direction, 0 meters per second squared. In the x direction, that's the direction of motion, and we calculated that to be 1.67 meters per second squared. And I'll put a plus here because it's to the right. I find it to be good habits to put plus and minus with your numbers just to keep track of things. And we also know the mass because we know that Fg is used to find the mass. Fg is always equal to mass times the acceleration due to gravity. That'd be true for every single problem. Some problems you're given the weight, as we are in this one, in newtons, and in other problems you're given the mass in kilograms, and you can find the weight by multiplying by 0.8. But in this case, I have the weight, negative 20, equals the mass times negative 9.8, the acceleration due to gravity. And when I divide, my mass is going to be 20 divided by 9.8 is 2.04 kilograms. So I can write that into my equation. 2.04 kilograms goes on both sides. So as we did with projectiles, once you have your table filled out, you can look at either side and say, hey, what pieces can I find? And because we only have one equation for each side, really I need to find the side that has one missing piece. Well, in this case, can find the applied force in the x direction because it's the only missing piece. So I'm going to set up Newton's second law, which says the sum of the forces. In this case, I have friction, and I have the applied force in the x direction. Those forces have to add up to the mass times the acceleration in the x. And when I plug in those values, I get negative 15 plus F in the x equal 2.04 times 1.67. And the only thing I'm missing is FA in the x, and I can solve for it. 2.04 times 1.67 gives me 3.41 on the right side. And I have negative 15 plus FA in the x. And when I add 15 to both sides, I get 18.41. So the applied force in the x direction is 18.41 newtons. So I can write that one right in here. So that's my x piece. Now the question asks for what the actual applied force is. Well, now if I look back at my trig, I actually know some information. I can take this piece and I can solve for the applied force. The applied force is going to be FA in the x over cosine of the angle. Well, I know those values. It's 18.41 over cosine of 50. 18.41 divided by cosine of 50 degrees. Make sure you're in degree mode, and I get a value of 28.64. The applied force is 28.64 newtons. So there's my answer for the applied force. All right, that's one answer. But they also want the normal force. They're looking for the normal force here. And if you look on the right side, well, we need to find FA and the y in order to get the normal force. Well, we just saw here that FA and the y is the applied force, 28.64 newtons, times sine of 50. And so since I just got that answer, I can take that answer and multiply it. Take the answer, second answer, times sine of 50, and that'll give me the y piece, right? 21.94. Now be careful. Look at my arrow that I drew. That y piece acts downward. And so it's actually, even though the trig gives me a positive value, I know it's negative because it's down. So in my table over here, when I plug in the y piece, I'm going to put in negative 21.94 newtons. Now, the only thing missing is the normal force, which means I can set up my equation just like I did on the x side, and I get Fg plus Fn, the y piece of the applied force. All three of those forces add up, the sum of those forces, the mass times the acceleration in the y. Fg is negative 20. Don't know Fn. Fa and the y is negative 21.94. We add all three up, and they equal 2.04. Oh, but it's times 0. So it's actually 0 on the right side, right? Because it's at rest vertically. And so when I add those pieces together, I get a normal force equal to positive 41.94 newtons, which makes sense. It's an upward arrow that's longer than gravity. And if you look at my picture, I actually drew it pretty well to scale. If gravity is that length, 41 would be about twice that. So as I zoom out, you'll see all the work. Again, this is a pretty complicated problem, probably a little tougher than what you guys would normally see or that you'd see on a test, but it really encompasses a lot of elements that you're going to see in these types of problems. So hopefully this is a good resource for you as you guys are trying to figure out how to solve these dynamics problems. Good luck.